Hello everybody, in this lecture we will be solving 1989 IMO problem number 2. Here is a view of this problem. I have a picture of this as well. So an acute triangle ABC is given. I have also the circumcircle of that triangle. We are told that the angle bisector, so this is the incenter of this triangle, the angle bisector AI meets the circumcircle at a point A sub 1, B1 and C sub 1 are also defined similarly. Let A sub 0 be the intersection of the ray AA1 with the external angle bisector at point B and C. So therefore you have A sub 0 as well. Similarly, B sub 0 and C sub 0 are defined, and you and triangle A0 B0 C0, yeah, this is a triangle obviously. One way to see it is that to recognize that angle IBA0 is in fact 90 degrees here. Angle IBA0 is 90 degrees. This is a very well-known property, so this is also 90 degrees. And that's also 90 degrees. So these are all straight lines. So A0 CB0 is a straight line. B0 AC0, that's a collinear point. C0 BA0 are also collinear points. Now we need to prove two results. Let's start with the first one. We need to show that the area of this big triangle A0 B0 C0 is twice the area of this hexagon inside the circumcircle, inscribed in the circumcircle. This is a direct consequence of the in-center excenter lemma, also known as Evan-Chen's fact 5. So I have a playlist about this celebrated lemma, which is very popular in competitions, in Olympiad math. So I leave it to you guys, but just be aware that because of this 90-degree angle, IBA0 is 90 degrees, it turns out that the A sub 1 is the center of a circle which goes through the points I, B, A0, and C. So what it means is that let me probably use some color here. Green might work. So these line segments measure the same length, and so there exists a circle going through these 4 points. So something like this, right? So these 4 points are concyclic by the by that lemma. So let's write that down. IB A0 C point. These points are concyclic, and the center of that circle is with center A sub 1. But what it means is that if you focus on on triangle IBA0, this right triangle here, BA1 is the median of this triangle. As a result, so BA1 is median in triangle IBA0. As a result, this would imply that the area of IBA1 is simply equal to the area of A1BA0, or if you will, that's also equal to half of the area of IBA0. That's a B here. But then, in a similar way, we can write each of these, so let's write that down. Similarly, IBC1 is simply equal to C0BC1, which is half of the area of IBC0 over 2. And I will just cut it short now. So it's therefore you can even combine it now. So it is obvious therefore that the area of IAC1 is simply equal to half of the area of IAC0, and IAB1 is equal to half of the area of IAB0. So for that, IAB0 over 2, and we have two more. ICB1 ICB1 is simply equal to ICB0 over 2, and finally ICA1 is simply equal to half of the area of ICA0. So now we can simply add the left hand and the right hand sides. Adding all the expressions in the left hand side, we will come up with the area of the hexagon, which is basically the area of this AC1BA1, AC1BA1, CB1, and adding all the expressions on the right side, we will simply get, I assume everyone is clear on that, A0, B0, C0, the area of here, over 2. But then I can now simply multiply both sides by 2, and I easily get the first result. So the first result is pretty easy using the in-center, ex-center lemma. So make sure to refer to those. If you are weak on this concept, go to my series about that topic. Now the second part of the question, the area of the triangle A0, B0, C0 being at least 4 times the area of triangle ABC. Let me go ahead and draw a new picture, I guess. That would make our life easy. So let's start with a circle, the circumcircle. Okay, and our triangle. Let's do it like this. So I have the base like that and like that. It's not the best, but it works, I guess. So we have still these midpoints here as A1. So this was a triangle ABC, A1, B1, C1, and what I will do next is I will actually do the following trick. I will focus on the orthocenter. So I will drop 3 altitudes and I will let them hit the circumcircle as well, and let's call these points as A2. No, I will call this one as A2. The foot of the altitude says A2, and I will call this one as A3. In a similar way, I will drop an altitude here, and so this is a 90-degree angle. I will call this one as B2, and this one would automatically become B3. And finally, I located my ortho center, and I connect it here. I have, this is the point H. That's a 9. This is C2, and finally this point here is C3. Notice that C1 is just the midpoint of arc AB. So why did I do that? As you will see next, I will make use of some inequalities. Let me use the red color. Consider the triangle BA3C. Using some angle chasing, it's not too difficult to show that. So claim, let's quickly do it actually. Claim, I'm sure I showed it in another video, but let's quickly do it. I claim that HA2 is equal to A2A3. So what I mean by that is that i.e. A3 is the reflection of H across side BC. One way to see that would be, as I said earlier, to chase some angles, and for instance, if you consider this angle is obviously equal to this angle over here, and that angle is also equal to this angle. Can everyone see why? Because okay, so this angle here, angle A3CB, subtends this minor arc BA3, but that arc is also subtended by angle BAA3. But then if you focus on triangle AA2B, this right triangle, you realize that this angle here is 90 minus B, but then flipping and looking at this triangle C2BC, which is also a right triangle, it's not surprised that this one is also 90 minus B. So therefore, so these two angles are the same. It's not difficult using a similar strategy to also see that these two angles are also similar, implying therefore that triangle BHC is in fact congruent to triangle BA3C. So therefore this would automatically give the desired result. So in a similar way, obviously, so these two are equal. In a similar way, this is equal to that, and this side is equal to this side here. Consequently, also you can say that the area of BHC is the same as the area of BA3C. Now, in the second important observation, and I say as a claim again, I claim that the area of triangle BA1C is greater than the area of triangle BA3C. And why would that be? Because A1 being the midpoint of arc BC, if I drop this altitude here, this perpendicular, and call this point as M, it's obvious that A1M, because A1M is greater than A2, A3, and they share the same base BC. As a result, BA1C is greater than BA3C. Therefore, we can come up with the following result. So the area of, quadrilateral HBA1C, HBA1C is equal to area HBC plus area BA1C, but I can this is the same as HBC. I can replace BAC with BA1C with BA3C, and I will make it smaller, less than or equal to, in fact, right? So I should probably say it like that, because there might be a case where A3 coincides with A1. So therefore, plus BAC1, I replace it with BA3C. But remember that these two areas were equal, so that's equal to 2 times HBC. In a similar way, quadrilateral HCB1A has area greater than or equal to 2 times the area of HCA, and also the area of quadrilateral HAC1B is greater than or equal to 2 times HAB. Now, we can go back to the original problem so the problem was saying that the area of triangle A0B00C0 is at least 4 times the area of our triangle. So let's start with A0B0C0. So the area of A0B0C0, well, from the first part of the problem, we already know this is exactly equal to 2 times the hexagonal part, AC1, BA1, CB1. We have proven this earlier. But that area is greater than or equal to 2 times. I can replace AC1, BA1, CB1 by 2 times area HBC plus 2 times the area HCA plus 2 times the area of HAB. Oops, like that. But that's simply equal to, so I can factor out further the 2's here, so I get 4 times, and HBC, HCA, HAB, they add up to give me the area of triangle ABC. And that solves the problem. Hope you enjoyed it, and looking forward to see you guys in our next video.